Welcome to this explainer. Okay, so have you ever really wondered how city planners, environmental scientists, or engineers determine exactly where to place a massive new highway or a wind farm without completely destroying the local ecosystem? It's a complex, multidimensional puzzle, right? Well, today we're going to unpack a foundational spatial mapping technique that actually solves this. It's called the overlay method. We're going to explore exactly how complex environmental and spatial data is organized to drive some absolutely critical, real-world decisions.
Here is our roadmap for today's session. We'll start by defining the overlay method, deconstruct the anatomy of map layers, and then trace its fascinating evolution from literal plastic sheets to modern geographic information systems. After that, we'll examine vector and raster data models, and finally, evaluate the method's advantages and limitations.
All right, part 1, the overlay method defined. Let's get our core concepts down.
So imagine you're evaluating a massive new project area. You've got to simultaneously consider physical, environmental, social, and aesthetic impacts. How do you wrangle all those competing variables? Well, the overlay method solves this by relying on a very specific set of maps detailing a project area's characteristics. Because think about it, instead of cramming a chaotic mess of information onto one single map, this method isolates each specific variable. Each impact gets its own dedicated layer. This creates a highly structured, wonderfully objective way to analyze geographic space.
Moving right along to section 2, anatomy of map layers. Let's visually deconstruct how this works.
Now, to truly grasp the power of this technique, we've got to look at how these isolated variables physically come together. This model from Dixon and Mons perfectly illustrates what is essentially a dynamic stack of information. If you start from the bottom, you've got drainage patterns, followed by land use, land stability, and income levels. Moving up the stack, we find air emissions, transport routes, and topography. By stacking all these vertical layers together, they synthesize into that topmost layer, the composite map. And this composite is a game changer. It reveals those critical intersections, like, say, where a proposed transport route might unfortunately cross over both a dense population center and a highly unstable land zone.
But here is the absolute golden rule for making this composite mathematically and geographically sound. Every single critical environmental feature has to be mapped at the exact same scale as the overall site plan. You literally cannot mix a super zoomed-in map of wetlands with a zoomed-out map of floodplains. It just doesn't work. Whether you're evaluating steep slopes, soils, or wildlife habitats, maintaining a uniform scale ensures that when an engineer places a building footprint onto that composite map, they are making an accurate one-to-one comparison.
Section 3, from plastic to GIS. Let's talk about the evolution of these techniques.
You know, the core logic of this method hasn't really changed over the years, but the execution, completely different today. Back in the analog era, planners would manually draw environmental features onto these transparent plastic sheets using different colored markers. They'd physically place these sheets on a light table to visually spot the dark, overlapping areas that indicated high environmental conflict. It's brilliant, but painstaking. Today, this exact same process is executed through Geographic Information Systems, or GIS. And GIS is far more than just software. It's an entire integrated system requiring specialized hardware, massive spatial databases, and skilled professionals who are trained to interpret these really complex geographic relationships.
Which brings us to section 4, vector and raster models, how we actually format this digital data.
Okay, so to really master GIS, we have to understand how a computer essentially thinks about something like a river versus, say, a property line. Notice how GIS takes our messy, continuous physical environment, the real world down at the bottom there, and it abstracts it into two very distinct data models, raster and vector. Every single layer we've discussed has to be mathematically translated into one of these two formats so the computer can process it. Let's break down why we actually need both. So vector and raster data serve totally different mathematical and visual purposes. Vector data utilizes distinct points, lines, and polygons. It gives you incredibly high precision for discrete entities that have clear, hard boundaries. Think customer locations, street center lines, or real estate parcels. Raster data, on the flip side, is basically a giant grid of pixels, where every single pixel holds a specific value. This model is absolutely ideal for continuous geographical measurements that blend across a surface, like elevation gradients or broad land usage types. To do comprehensive spatial analysis, you absolutely have to seamlessly combine both of these models.
All right, Section 5, Advantages and Limitations. Time to put our critical thinking hats on.
Just like any scientific framework, the overlay method has its absolute strengths and, of course, its blind spots. Looking at the advantages, planners heavily rely on this method because it is highly intuitive. It provides a phenomenal visual display. I mean, seeing 3 dark overlapping colors instantly identifies a high-impact zone, which makes it exceptionally good for initial site selection. However, the academic limitations are pretty significant. The method primarily addresses direct impacts, like a road physically cutting through a forest, but it completely fails to address impact duration, like how long will that ecosystem actually be disrupted, or probability, what are the actual statistical odds of a flood occurring there. Simply put, it tells us the where, but it really struggles with the when or the how likely.
And that brings us to Section 6, Summary and Final Thought. Let's wrap this up.
Let's synthesize what we've covered today. Our core takeaways? The overlay method is an absolutely essential technique for mapping diverse environmental characteristics at a uniform scale. We saw how it evolved from physical, transparent plastic sheets into the incredibly powerful multi-layered GIS technology we use globally today. It relies on both vector data for precise boundaries and raster data for continuous gradients. And finally, while it remains a top-tier tool for site selection, its static nature means it inherently ignores the duration and probability of the impacts it's displaying.
Before we go, I want to leave you with a final thought to chew on. We know the overlay method excels at revealing spatial intersections, right? But it falls short on time and probability. So how might modern planners and engineers compensate for these critical blind spots in their final assessments? Consider how dynamic simulation models or advanced statistical forecasting might actually be integrated into these static maps to create a truly predictive living environmental model. Something to think about. Thank you so much for joining me in this explainer. Keep analyzing those layers and I'll catch you next time.